This is problem number 19 from section 3.3. I've attempted to bring in a copy of the problem from the book. I hope it helps. Our system is given like this, and I rewrite it as a matrix. And I won't show the calculations, but we find two eigenvalues, a -1 and a -2, and their corresponding eigenvectors of 1, 2, and 1, 0. The fact we have two negative eigenvalues means that along each direction, we're always moving towards the origin, and therefore the origin is a sink. So our equilibrium point is a sink. Next, it says calculate all straight line solutions. Well, these are our straight line solutions, e to the minus t, 1, 2. So anything that lives along this line, any vector we write along this line, which will be in this form, will solve this system. And I don't have enough room to demonstrate that, but that is absolutely true. And similarly, anything, any function of this form, pick any value of k2, that'll put you somewhere on the x-axis, and as time evolves, it'll move towards the origin, and that also will satisfy the linear system. Part C says plot the x of t and y of t graphs for the initial conditions at A, B, C, and D. So essentially, I'm just going to be following the straight line solutions. I'll be following the phase plane to do that. So let's start with at point A first. Here it's so close to the equilibrium point, it's hard to make many distinctions about the direction, but we can see as we look at the little slope fields that as time evolves, it has to approach the origin parallel to y1, and that is because the eigenvector associated with lambda 1 is smaller than the eigenvalue associated with lambda 2, and we will always approach the origin parallel to the direction of the smaller of the two eigenvalues. Similarly, point B, we see this is where we're starting, and we're moving in. Oh, we get a color. We're starting at B, and we're moving in and approaching the origin in the direction always of y1. C is coming around, approaching like this, and D, well, D lives on the x-axis, and so it approaches the origin like this as time evolves. That's it. Thank you.